Hi, my name's Mike Bussell. I am a Chief Security Architect, as part of the Office of the CTO at Red Hat, and I'm here with Nathaniel McCallum.
Hello, everyone. My name is, as Mike said, is Nathaniel McCallum, and I am the Virtualization Security Architect at Red Hat.
And we are co-founders of the NARCS project. And we're here to talk to you today about confidential computing across multiple clouds and platforms, which is Project NARCS. We really welcome questions as we go through. Please put stuff in the chat, and we'll try and answer those as we go. I'm sure you can find us elsewhere if you need to get a hold of us. So without any further ado, let's carry on. So first of all, we've introduced ourselves. We should be clear that NARCS is a team project. It's an open source security project, and so although Nathaniel and I are the founders, lots of it has been contributed, coded, and documented by other folks as well. And we should also say it's open source, uses trusted execution environments. It's not the basis for a product yet. Hopefully that'll change. And this is not a product pitch. We're not trying to sell you a product, because this is a technical session, and we hate product pitches at conferences, and we think you deserve better. Oh, and of course, it's not a product anyway. So let's get on and explain what we're talking about. So first of all, what is the problem that we're trying to solve? Well, it's about risk, it's about trust, and it's about isolation. Or another way to look at it is not everything in the cloud is a good thing. So Nathaniel, why don't you talk a bit about workloads?
Sure. So there's been a lot of excitement about moving to the cloud in recent years. Of course, Mike and I share this excitement, but it also brings a lot of challenges, particularly for the type of workloads where you have to have either sensitive data or sensitive algorithms, or where you have to make sure that you are managing risk or are handled by governance or regulatory environments. And so this is precisely what we are targeting. Examples of sensitive data might be things like credit card data, firewall configs, administrative passwords, or CEO compensation. All of these kinds of things are sensitive data that you don't necessarily want anyone looking at, and there comes additional risk if we try to put this in the cloud. We also have sensitive algorithms. For example, this is really big right now in the AI and machine learning disciplines. We have a lot of new algorithms being generated, and these, it would be risky to expose these to other competitors, for example. But other examples for this include things like financial models or pharmaceutical research. All of these are sensitive algorithms, and you don't necessarily want to disclose the actual code that you're running in a cloud environment. And then finally, when you do have risk management in government or regulatory sectors, we need to be able to provide cryptographic evidence that the environments that we are attempting to run our workloads in are protected against tampering. And these include things like in the GDPR space, the telco space, HIPAA, or really any healthcare regulation, and even things like Sarbanes-Oxley, for example. And then a lot of this just also boils down to your reputation. So if you have an important reputation or an important brand that you don't want to tarnish with an accidental disclosure of sensitive data or algorithms, then this is a concern for you. Mike?
Yeah, sure. So let's talk briefly about isolation. So let's imagine a simple case where you are a tenant and you are deploying a workload to a host, and the host is in a public cloud, AWS or Google or IBM or Azure or Alibaba or whatever. But you're running a workload, and there may be other workloads on the same host. So you really do not want those other workloads interfering with your workload. So luckily, that's something that we know how to do. The industry's been doing this for 15 years or so, maybe more, with blocking workload from workload attacks, confidentiality, integrity, all those sorts of things. We know how to do that with hypervisors and containers and those sorts of things. The second type is host from workload isolation. So the cloud service provider running your host really doesn't want you breaking out and attacking their host, because once you've done that, you can attack the rest of their infrastructure or other workloads. And again, actually, this is something that the industry has been dealing with for quite a long time. Same sort of things, hypervisors, SE Linux, SecConf, a number of ways of dealing with those. But there's a third type, and that's workload from host isolation. And this is exactly what we've been talking about, where you need to protect your data from the host itself. You may not trust your cloud provider, or you may be running on an edge machine where it may be vulnerable. So how do you protect the workload from the host? Well, in current computing models, you just can't. Memory pages are mapped by the host OS, by the hypervisor, by the container runtime, and you can't protect against them. So we came across a while ago an excellent XKCD cartoon where it looks at all the different levels of the stack, and to be aware that hopefully not all of them will be compromised, but there are opportunities for compromise all up and down the stack. And the problem is that once a level of the stack below you is compromised in the current model of computing, there's very little you can do about it. And in the cloud, you need to worry about other workloads, your sysadmins, the CSP's sysadmins, OS compromises, government agencies, all those sorts of things. On the edge, you've still got similar folks you need to worry about. So what's the answer? Well, the answer, or part of it, is trusted execution environments. Do you want to talk about this, Nathaniel?
Sure. So the major development that we've seen in recent years regarding trusted execution environments is the ability to isolate and usually encrypt memory when an application is running. So an application is able to run, its memory pages are able to be encrypted while it's running, so that you can theoretically not have disclosure of your data. And there are a number of hardware providers that are providing technologies in this realm. For example, one of the earliest ones was ARM TrustZone, and that was targeted towards the mobile device market. And then Intel responded with a technology called SGX, and then others have been developing as things have gone along. We've seen, for example, a shift for at least a part of the market into encrypted virtual machines. The examples of this are AMD's SEV technology, which is the most well-known and is broadly available today, at least in silicon, and TDX from Intel, which has been announced but is not publicly available yet, as well as PEF from the IBM Power Group. Similar to that is the RISC-V Sanctum, which has a similar profile as TrustZone and SGX. And so there's been significant amount of work in this, including the creation of a consortium in the Linux Foundation called the Confidential Computing Consortium. And they have defined this problem set as the confidential computing is the protection of data in use by performing computation in a hardware-based trusted execution environment. And the features for this may include things like integrity and confidentiality protection of the memory pages of the application at runtime. This includes the data and the code that are in those pages that are therefore protected. And then very importantly, and this is something that we want to emphasize a lot, is attestation. And attestation is a cryptographic process where we can validate with cryptographic evidence that a computing environment has been set up according to the specifications that we have requested. And so this gives us measured cryptographic proof that that a cloud environment has not been tampered with, and that only the desired actors can have access to it. A key point here is that the memory page access is protected by the hardware. So that may include things like denying it or only providing access of ciphertext. Different hardware technologies take different strategies here, although everyone is sort of moving slowly towards denying access to the protected pages as well. So we'll see some more maturity in that as the market itself matures. But this is essentially an overview of the players and what they are attempting to accomplish. Mike?
Yeah, and so this is exactly what we were talking about in that third type of isolation, where we are isolating the workload from the host, because what this technologies allow is for you to run your workload in such a way that the host, the hypervisor, the kernel, super admins, administrators, whatever, cannot look inside and see what you're doing. So TEs sound great. These trusted execution environments sound great, but there are some problems with them. The first one is that we listed several platforms on the previous page, and in order to create an application or make your application run in those, you need to be developing it differently. There are different libraries, there are different models for how that works, and that's a real pain. So in order to try and deal with that, people have written SDKs, but those SDKs restrict what languages you can write in. So if you've got something which is already written, but in a language which isn't supported, or you have a preferred language in your organization, and that's not one of the ones that's supported, you've got a real problem. The other thing is this issue about attestation that Nathaniel mentioned a moment ago. You need to be absolutely sure that you are deploying your workload to a place which is a real and not a spoofed environment. And that's really tricky. And all of the different technologies have different ways of doing it. And last thing, of course, is that you've got different vendors, and obviously there's going to be some vulnerabilities discovered in these. We've seen a bunch of these published over the last 18 months or so. These will keep happening. They'll keep being mitigated and patched, etc. But you need to worry. You need to worry about how you're going to address these with actually with applications that you've actually deployed. So what happens if you just want to deploy workloads? You don't have to worry about all of these things. You don't have to worry about these things if you're writing a VM or a container at the moment. Why would you complicate your life when you move to TEs? So one way to solve the problem is to let your CSP solve it for you. There's a number of ways of doing this. Why don't you talk about what they are, Nathaniel?
Yeah, I think it's important to note that these are all real-world examples of how existing cloud providers are attempting to solve the problem of making trusted execution environments usable. And they all have a number of problems. So, for example, there are mechanisms which allow you to take an app and then it will recompile or rebundle your app. And so it basically modifies your app before you deploy it. This has a significant downside for attestation because how do you know that they're modifying your app in a way that's trustworthy? And how can you validate that through attestation? So that's a difficult problem, and it means that you have to trust your cloud provider, which one of the entire points of TEEs is to actually remove the host operating system from the trust chain, remove the host provider from the trust chain. So this puts them right back in. So that's the attestation piece. But one other problem with attestation is that a number of cloud providers are also building attestation services. And so they want to make it easy for you to consume their attestation model. And the way that they do this is by building an attestation service. Now you can run your code and the attestation service will deploy it. And if you ask the attestation service, it'll say, oh yeah, I checked the attestation. It's great. And we think that this is insufficient. So we don't want the cloud provider to be doing the attestation on our behalf. Again, one of our goals is to remove the cloud host from the trust model. Another problem is the question of how you prepare your VM. Today, there is not a virtualization product which allows which has a stable interface between the virtual machine manager or hypervisor and the guest kernel. So even though you as a tenant may provide a kernel, you can't provide the BIOS. The BIOS comes from the host side, which again allows the host a footprint inside of your trust model. And this is the very thing that we are trying to get away from, and is going to be difficult with virtual machines. And then finally, there's another set of CSP deployment mechanisms where essentially they will build their own parallel root of trust on top of this, which again requires you to trust the hosting provider in order to have this solid root of trust all the way through. But we already have a root of trust, and we have it directly to the hardware. So what we want to do is we want to go directly from the hardware root of trust. We want the host operating system to be completely out of the trust model, and then we want the tenant's code and data to be the very next thing that's part of the attestation. So this is why we have this problem, that it also completely misses the point, because if we're solving these problems by just adding the additional footprint for the cloud service provider into the trust model, we've just essentially broken what the TEEs are actually promising us that we can do, which is run code on someone else's system without having to trust that party. And excuse me. So Mike, would you advance it one more time? And of course, as soon as we allow the CSP into that hosting space, the problem that we have is lock-in. And this time it's cryptographic lock-in, because every time that we want to deploy a workload onto a host, it's going to be a different measurement, because it's different. It's a different cloud service provider. And we want portability. We want to be able to take a workload. We want to be able to have it on one host, move it to another host dynamically. We want this to be able to be done in minutes, rather than days or weeks or even months. So we want to avoid this problem of lock-in. Mike?
Yeah, so I kind of think of this like when you need your car service, you want to make sure it's roadworthy. You take it to a garage, and they say, yeah, I fixed it, but I've used all of my own stuff, and I've used my own wrenches and spanners, so you have to come back to me. And yeah, you trust me, I tell you it's fine, but you have no way of checking. Because everything is in their hands and they sealed everything up. And that's the opposite of the way we think we should be doing things. So let's introduce NARCS, which is an open source project which aims to fix many, if not all of these. What does it do? Well, it uses trusted execution environments. We're trying to make it easy. It has a very strong security model. It's cloud native, and it's open source. So we plan to support as many of the trusted execution environment platforms as we can. We want to make it easy to deploy and develop. It's part of the Confidential Computing Consortium. And as I said, this is a project. It's not production ready yet. So here are our design principles. Nathaniel, this is your slide. Go for it.
Yeah, so one of the things we aimed to do when we set out this project was to put a stake in the ground philosophically, that we wanted to commit to a very high set of design principles that we did not see being implemented elsewhere in the industry. And we have these 10 principles. So number one is the minimal trusted computing base. We want your workload plus any hardware enablement code that gets bundled with NARCS, which again is all open source and is provided by the tenant. And then we want the host CPU and firmware, right? That's all that we want in the trusted computing base. So we're aiming for something that is very small. We also want a minimum number of trust relationships. If you're deploying any sort of workload, you have to trust your CPU manufacturer. There's simply no way around it. You also have to trust the firmware that they provide, because it's essentially part of the CPU these days. So this is the very minimum set of trust that you can have to do any computing in a first principles design. So what we don't want to trust is we don't want to trust things like the host operating system. We want the tenants to be able to provide all of the bits that are part of the execution environment. And therefore, the tenants can validate these according to his or her own policies, whether they're individual or corporate policies. So, and we don't want to involve lots of other trust relationships in this and other parties. We don't want complex certificate chains that are signed by lots of different people. We want it to be as simple as possible. So number three is that we want deployment time portability. So when you take an application and you compile it and you deploy it, we want to be able to take the same compilation artifact and we want to be able to redeploy it across a number of CPU architectures. This is particularly important as we invest additional trust in the CPU So, for example, if meeting my regulatory guidelines, whether they're GDPR or Sarbanes-Oxley or PCI DSS, if meeting those requirements is a matter of doing my business and not getting very large fines, then one of the things we need to do is we need to be able to take a workload from a vulnerable CPU and move it to a CPU that's not vulnerable. And so this is why deployment time portability is important. Not only for being able to migrate a workload to where it's the lowest cost, but it also protects you from vulnerabilities in this new age of TEEs. Number 4, we want the network stack outside the TCB. If you look, for example, at the Linux kernel, and I'm not picking on anyone here, if you look at pretty much any kernel or low-level embedded infrastructure, you'll see that a large number of the serious vulnerabilities come from the network stack. And one of the things that we are aiming to do is we're aiming to move all the parsing for all of that network I/O outside of the TCB so that a vulnerability does not result in a compromise of the TEE. Number 5, we want to ensure security of our data and code at rest, in transit, and in use. So this is something that's difficult to do in today's environments. While it's true, applications can, depend on libraries like OpenSSL and can bring up TLS connections. While it's true that deployment, that a deployer of software can try to enforce things like data encryption at rest, these are all piecemeal solutions, and they depend upon multiple different parties integrating them correctly. And then you have to have complex management of the keys for everything that's involved on top of this. Even though you're using different products for different things. But one of the things that we recognized with TEEs is that because we can encrypt the application as it runs in its memory pages, if we have a way to also enforce that all of the persistent storage and all of the network traffic is also encrypted, then basically we have a system that once the data enters it, it stays encrypted through the entire lifetime of the system, and it's never decrypted. And this, we think, is an important security property. So number 6 is the principle of auditability. Everything that we do, all the code we write, we aim to be easy to read and auditable. We want it to be simple. We want it to be straightforward. And of course, that leads us to number 7. We want it to be open source. We believe that a significant amount of the trust that you have when you're deploying code, it depends on your ability to evaluate the code or to submit it for third-party evaluation. And so 6 and 7, auditability and open source, are incredibly important. Number 8, we don't want you developing applications to NARC's APIs. We're not interested in that. What we do care a lot about is open standards. So what we want you to do is we want you to write an application in the language you care about. We want you to compile it to WebAssembly, which is a neutral compile target, which can be just-in-time compiled for any CPU architecture. And we want you to use the WASI APIs that are a part and currently being standardized for WebAssembly. And all of this is just simply standards compliant. You're not building something on NARCs. You're just using NARCs to deploy a standards compliant application. Number 9, memory safety. We care a lot about memory safety. So all of our code is written in Rust. We do have to have a little bit of assembly because we have to get the hardware to work, but almost all of it is written in Rust, and we take a strong emphasis on memory safety. So we limit the number of unsafe blocks, and we try to do things as safely as possible with a memory safe language. And number 10, we have a commitment to no backdoors in the project. So we will never merge a code that has some kind of a backdoor from any sort of third party. So those are essentially our design principles. We hope we've hit all the right points. And if you'd like to offer us feedback, we'd love to hear it. Mike.
Yep. So you've hit everything already. I won't go on this. WebAssembly, that's the runtime we provide. It's all in Rust, and we go with various types of TEs. So it's time for a demo. Let's do a brief demo, and let's see what we have here. Okay, so I need to go from the beginning. Right. So I'm going to show you deploying an actual application. First of all, we need an application to deploy. So I'm just going to clone a very simple application and show it to you. So it's written in Rust. Here we go. It's very simple. It creates a random number, puts in a string, and it waits 20 seconds before showing it. That's all it does. It's very, very simple. We're going to build it, but we're going to build it to become a WebAssembly application. So as we said, that's what we want to be running with WebAssembly. So now we need to deploy it. This is as if we're on a client machine and we want to deploy it to a server. So that's the deploy verb there. Where are we going to deploy it to? Well, first of all, we need to decide what to deploy, and that's the thing we've just created. That's the target that we've just done, the .wasm file. There we go. And we're going to deploy it to a machine called roam.sev.lab.narcs.dev. And there should be hopefully something running on 3030, ready to accept it. So there we go. We're running that machine, that server on that machine. Okay, so before we do that, we're going to need some way to look at the output. We're going to run this low level in journal.cutl. But also we've got a nasty little thing which is going to try and do a bad thing. So we're going to run the application. It's being deployed now. Excellent. It's been sent. And if we look here, we have created that secret. So now we've got this other application which is going to try and look at it, and it's actually found it. Let me just stop for a moment. So the application on the bottom right is an evil application which sits on the host, sits on the Roam machine. You can see it says Roam there, and it searches the memory pages associated with that application. So this is not a good thing. It's found that sensitive information. It's found that those firewall rules or those cryptographic keys or your CEO's information, and that's a bad thing. So how did that happen? Well, the answer to that is we didn't send it. We didn't deploy it to a TE. We deployed it just as a standard WebAssembly workload running as a standard binary. And that's what we found. We found that because it was not protected. Okay, so let's...
And this is what you get, by the way, with every workload you're deploying today. Every workload you deploy today with sufficient privileges on the server side, an attacker can scan the memory and extract those secrets. So this is the state of the art before NARCs.
Absolutely. What we're going to try now is deploying it to KVM in a VM and see if the VM, deploying a VM gives us any more protection. So we've done that. It's created the secret. And it's running in a KVM, virtual machine, and now we're searching for it. And let's hope on this occasion that the VM will give us some more protection. Is it going to give us any more protection? Well, I have my doubts. Let's see. It's waiting for those 20 seconds, and it found the secret. So this shows us that VMs do not provide that isolation. Now we're going to deploy it to an SEV, Trusted Execution Environment, keep. We call it a keep where we run stuff. So we deployed it. There we go. You can see it's been created on the top right. It's been sent on the bottom left. And it's created. Let's see this time whether our evil secret search can find it. I should be very clear that we've run this fully attested. We did all the cryptographic checks before we even sent the workload. And once having done so, having done those checks, we sent it encrypted. So at no point was it visible to the host, and it's worked. The secret search was not able to find it because it was protected by the trusted execution environment, which is exactly what we hoped for. So what you've just seen there was NARCs taking a workload and deploying it first unprotected at all and showing that indeed it wasn't protected. Second, deploying it in a VM, which is the standard way you generally be deploying stuff in a cloud or in a container. It makes no difference in this case. And showing again it wasn't sufficiently protected. And the third one was when we actually deployed it into a keep using NARCs, attested, and using a trusted execution environment. And there we saw that it was protected. We're running pretty short on time, Nathaniel. Do you want to quickly just talk about this, this stack?
Yeah, so this is basically an architectural stack of our various layers. On the bottom side, we have different kinds of keeps. Keeps are what we call our trusted execution environments. On the left, we have SGX, and we don't currently support RISC-V Sanctum, but we're showing that it could go there. On the right, we currently support SEV, and we are working towards PEF and TDX. But then on top of that, you get a WebAssembly layer with WASI. These are your standards that are being built as the base API. And then above this, you get your language bindings and your applications to pretty much whatever language you want to run in. All of that is built on top of open standards.
And the key point being here is that the application doesn't care what it's running on. We talked about deploy time, provisioning time, neutrality, and portability. It doesn't care. You write the same application, you deploy it to whichever, and NARCS handles all of the messy stuff underneath. So this isn't the only way you could do it. Let's just quickly discuss these, I guess, Nathaniel.
Yeah, so there's a variety of other approaches. Like Mike said, NARCS is not the only one. For example, there's SDK-based approaches like Fortanix and OpenSDK. There are ELF-based, they're focused on running Linux binaries. These also go under the name libOS sometimes. But the idea is basically like with Graphene and Mistros, which was recently announced by Azure. The goal here is to run existing Linux binaries, and there's various trade-offs for that. And then finally, there's various libOS methods. Like, for example, Rust has like native support for running or for compiling applications on top of SGX, and that's just built in part of the standard library. So it allows you to sort of do that on a language-specific basis. Michael.
Sure. So we're getting to the end now. What should you do having watched this? Well, hopefully you've been asking us questions. You can always find us. We'd love to talk to you. But what can you do? Get involved in the community. Try NARCS. It's at the stage where it's very close to being something you can try. By the time this is going live, hopefully you can. Get involved in the development. And if you're interested in confidential computing more widely, you can join the Confidential Computing Consortium or just attend the meetings. You don't need to be a member of the Linux Foundation or the consortium to attend meetings. You're very welcome to the technical or any of the other meetings. From a business point of view, think about what your organization's sensitive workloads are. What are they? What do they need in terms of resources? And what things do they trust? And what should they be trusting as you deploy them? At the same time, you could think about the impact of your GRC and think about, okay, given you've got these three workloads, maybe two of them are financial and the third one has a HIPAA requirement. Think about the different requirements they meet and then tell us. We want to hear how you would like to use this technology, how it could help you. We've got loads of use cases, but we absolutely want more. So last slide. Is how to get in touch with us. Well, first of all, if you go to narcs.dev, you will find all of the code. You will find a wiki all about it. You contribute. There's the Git there, loads of information, design documents, and we'd love to see you. And of course, you can join us on our chat. It's a rocket chat at chat.narcs.dev. Very friendly. Join us, and we'll chat with you. And as I said before, we're part of the Confidential Computing Consortium. So please join us and come to the meetings there and find out more about the broader work that the consortium's doing. So that's it from me. Anything you want to finish with, Nathaniel? I think we've covered quite a lot pretty quickly.
Yeah, I know it's been a bit of a fire hose, but thanks for attending the presentation, and we hope we've given you something interesting. It's always a pleasure to present these, so thank you very much for your attending, and we wish you best of luck.
Thank you.